So we're going to be talking about agent spatial embedding in landscapes, and specifically going into the issue of agent mobility. So spatial embedding of agents is a key mechanism of interest to capturing certain health dynamics within models. So, for example, if you want to express certain essential dynamics, say the spread of a prion-based disease, like we've just seen, you really need to capture spatial representations. The fact that it's concentrated in certain areas and less so in others. If you want to capture locality of influence, the fact that people co-located, if you have A co-located with B, there'll be more influence between the two in terms of shaping knowledge, attitudes, beliefs, norms, etc., than if they were some distance from each other and not directly in contact. So capturing imitative behavior, capturing the ways in which one person shapes the behavior of another, spatial proximity is important. And spatial embedding can be of quite central interest for certain types of problems where GIS systems are used, geographic information systems. There's three types of spatial support provided by AnyLogic. One is continuous embedding, one is GIS embedding, and one is discrete cells. GIS embedding shares a lot of features with continuous embedding, but it has some additional types of information it can maintain. You can load in GIS shape files, and you can easily associate resources with some of the shapes that result. So with AnyLogic, you could represent, say, the location of resources associated with certain features captured in GIS shapefiles. And it allows you to keep information on things like heading, agent latitude and longitude, etc. Okay? Continuous embedding and discrete embedding, I therefore want to distinguish from each other because GIS shares so many features with continuous embedding. So there's two basic modes for embedding agents in AnyLogic. In one case, we have space divided up. The technical word is tessellated into these squares. Space is divided up into a grid of rows and columns. And each person has an X value, but they have a row, more importantly, or a column associated with them, and they have a Y value, but also a row associated with them. Okay? And a key constraint here is that there's only one or zero agents in a given cell at a given time. Okay? So there's only up to one agent. This should really say only up to one agent. So only zero, or one agent in a cell at a given time. Apologies about that. So here we have these rows and columns. They form a grid of spaces, a little bit like the patches. If anyone's used NetLogo before, you have sort of these patches. And here each patch is either zero or one agent. It's either empty or it has an agent in it. Okay? There's mutual exclusion. Think about lots in a city. City lots with houses, or it's a house, or it's it's a commercial real estate, or it's a park, or it's a brownfield and empty, but they're mutually exclusive. That's the idea. By contrast, in continuous embedding, and by extension GIS embedding, you have, it's assumed that you're viewing the space in a way at such a level that really there's not exclusion going on. In other words, agents seem to be very small compared to the landscape scale. They exhibit arbitrary density, so they can pass one another without directly, blocking each other or what have you, and you don't have this mutual exclusion. Okay, and we've seen some of this already with distributing people around the space. Okay, so within AnyLogic, there's a variety of features you probably have noticed already associated with setting up a space. So if we go to main here, and we go to down to here, we could specify a continuous space, a discrete space, or a GIS space. If we specify discrete space, for example, we need to specify not only the width and height, but columns and rows, whereas a continuous space only has these width and height relevant to that. Discrete is 2D, continuous can be 3D. And GIS space, we can draw information from a GIS map, okay? So here in continuous space, there's no division into rows and columns. Instead, people, again, don't have mutual exclusion. You can also further specify for discrete space, I should have emphasized this, for discrete space, we can specify a network or a topology, a neighborhood type to use, either more neighborhood where we have 8 neighbors. So we have, I may have a nice little illustration of this. Certainly the AnyLogic help has, so neighborhood, more, and then Euclidean. Oh, let's try that again. Okay. Oh, neighbor. Thank you. Not neighbor. More and this should be. Hey, come on. Neighborhood. Oh man. Neighbor. Oh man. This is neighborhood. Okay. There we go. Discrete space. This is what we want. And here we have 4 neighbor cells: north, south, east, and west. Whereas with the more neighborhood, we have 8. Okay. So with even though we're surrounded by 8 cells here, we're only considering the cardinal directions: north, south, east, and west. With more, we're considering all 8 directions. Okay. And that influences who's considered your neighbor for the point of view of influencing them. Okay. Okay. So we're going to actually go and implement some models within the continuous space, and as time allows, we may look at a model in the discrete space that I've provided to you just recently since we came here on the Google Drive. Okay, so I'd like you to go and close whatever models you have open, okay? And the first one was, we're going to use this to show aspects of embedding and mobility. I'm going to kind of weave the two together. So we're going to create a totally new model, and the basic steps will be the same as before, okay? We're going to create a new model, and this is going to be called simple agent movement, NC, okay? And here we're going to be adding a new person, a new agent, okay? This should be really familiar. So I have a person, yeah? And this person is going to be associated with characteristics. We're going to make them, this won't be very material. I'll make them an oval. You may want to use other icons. We'll make them an oval here, okay? And what we're going to do is we're going to basically have them move around. So that we're not going to give them any fancy characteristics, but I'd like you to go up to main, and we're going to set it so when we click, and we're going to create a population of these agents. Let's do that in main. So create a population here of size 100. That should be fine. And by creating this population, we're going to lay them out randomly. Okay, and you can do it in the standard way, or the earliest way we learned. So down the layer type, we're not going to be adding any new agents here. So you can go down to random, down to this. Okay, and here we go. We should see something like that. Are people okay with that? Who needs TA help? Okay, so what we did is we put person, in person, we put this, we went to main, we added a population, and we set it to be a population of agents of size 100. Okay? And then finally we went to main, and we set them to be randomly laid out. People comfortable with that? Okay. Okay. So now what I'd like you to do is to do the following. This will take us into uncharted territory. Yeah. Okay. It's in main, and you scroll down to the area that says environment for other agents in main. So it's yeah. Okay. Layout type random, right? Yeah. Sure. Oh, do we have something exciting? Oh, neat. Okay. Oh, great. Okay, save the model so I can look at it. Oh, wow. Yeah. I haven't seen that in a long time. Okay, that's neat.
But do you want to save the screenshot too?
Oh, yeah, that would be beautiful.
Yeah, so give me one chance.
Okay.
Oh, no, it made it. It went. It went away.
But like 5 times like that before.
So you lost the chance to save it.
Okay. Okay. But
no, the linkages are not. Nothing has been created. That's why you are.
I see. Okay. Okay. Yeah. I've seen that. No. Okay. If I were, yeah, might close AnyLogic and come back into it or something. But anyway. Okay. So, folks, we're going to go add to main. We're going to add a rectangle. And this will be something we're going to click on. And we want just a surface we can click on. And I'm going to set in the properties of the rectangle here, I'm going to set its width to be 500 and its height to be 500. Okay? So it's going to be the same size as the space in which people are embedded. So how did I do that? I went to main, down to this presentation palette. I went to main, and down this presentation palette, I dragged the rectangle up here, 500 by 500. Okay? And then, this is very important, folks, that this particular step, you're going to go to main and then add a rectangle, and the width and the height of the rectangle will be 500, and then right-click on the rectangle and do send to back. So the rectangle occurs behind the agents that will appear on it. Okay? So I'd like you to run this now and just make sure that the agents appear atop the rectangle. You should see something like this. Who needs TA help? Who needs professor help? Okay. Yeah.
No, I don't have the model open population open.
Open population. Building model open population.
That was an older model.
Oh, were you running it through this?
Down here.
Or, okay, through this? Mm-hmm.
Okay, the same error.
I think it's because if you run it up here,
I thought if I clicked on it and then pushed the run button.
No. Okay, yeah, maybe I'll make a general announcement because I think this is a affliction troubling many people, and it's timely to give a warning. So, folks, I've noticed informally that a number of the problems people have encountered very reasonably have been linked with pressing this button up here. Okay. This button up here is a little bit confusing because it runs past scenarios that you have run. Okay, in many cases it's loaded with past scenarios. So if you go from one model to another model, suppose I were to go run. If I were to close this model for a second. And I'm going to open a previous model, and I'm going to run it, okay? I'm going to just open a continuous aging. Here we go. And I'm going to run this one. And then I'm going to go leave this model, close it. So here we are. We're running this model. Things are happy. I run it, and now I'm going to close it. Boom. And now I'm going to load in a new model. I'm going to load in this simple agent movement. Okay. Now you'll notice, okay, I suspect that what's happening is when this is being pushed, that sometimes it's trying to run the previous one. The strong way I'd suggest to run it is by right-clicking here. It makes it very clear exactly which one you want to run. I think there's something going on when you switch models with this guy preventing it from running. Okay? I don't have the smoking gun yet. I'm looking for it. But anecdotally, a lot of problems are associated with this. And it's not the same. If you click on this and run it, I don't think it understands that you're trying to run that. The best thing to do is to right-click and run it. So you should see something, for this model, you should see something like this. Okay? People okay with that? Okay. Now we're gonna do the kicker. We're gonna do the clicker. We're going to go to main, and we're going to click on this rectangle, and we're going to go do something. We've done something like it before. Down in the advanced area of the rectangle, I'd like you to find the on-click handler, okay? Okay. And it's at the on-click handler that I want to do something unusual, okay? We're going to get each agent to move in a certain direction, okay? So we're going to write something here that is going to get all the agents to move towards the location of the mouse, okay? And we'll see the behavior associated with this. This will illustrate the basics of movement, okay? But to help motivate why this code is being written the way it is, I'd like to do an intermediate step that is going to take a little bit less work. Go up to person, and I'd like you to open the presentation there, and I'd like to do a similar thing here. Under on-click, we're going to write a bit of code. Here click on the person, and we're going to write this dot move to, and this is the new thing, move to, and that's going to move. We can move to an X and a Y location. Okay, we're going to move to a location whose location is randomly. It exhibits a normally distributed perturbation to our current location. So it's normally distributed around our current location. So it's going to be moved to the X location. We have to say move to, we have to give it information to do its work. What information do we have to give it? We have to give it information on the X and the Y coordinates. So for the X coordinate, we're going to have draw from a normal distribution with a standard deviation of 100, and a mean of our current location. Okay? And similarly, for the Y value. So it'll be get Y. So this is what I'm writing there. Move to of this thing. And this will help us understand when we do the other one why we're writing what we're writing. Okay? It goes in the on-click for the person's circle. It's down in the advanced area. You see that?
Yeah,
on-click. Yeah. Okay? So what this is saying is, hey, let's move them to a location. Well, which location? That's great. Move to needs two things to be given to it to do its work, an X and a Y location. What's the X location? The X location is going to be determined by this draw from a normal distribution. It's going to draw from normal distribution with a standard deviation of 100 and a mean equal to get X, the X of the current agent. And similarly for the Y location to which to move, we're going to draw from a normal distribution with a standard deviation of 100 and and a mean Y value given by our get Y. So it's going to, it's going to take a normal distribution sort of surrounding ourselves, and going to use it a bivariate normal distribution with standard deviation 100 to 100. The covariance matrix is going to be diagonal with 100 and 100 in it for the standard deviation, and the square of that for the variance, and so it's going to draw from a bivariate normal distribution around the current point. Okay, does that make sense? So we're going to click there, and it's going to pick a point to which to send us. Okay, can we run this? Are people comfortable, or do you want to see that more? You want to see it more? Build early, build often. Okay? Can we run it? Okay. So what's going to happen? We don't see anything happening. What do we need to do? Click. Look at that. What's going on? Click another one. Click another one. You want to speed it up? You can speed it up this way. Woo. Well, you can jump to or you can move to. And let's illustrate that, okay? This looks like, what, a game of sort.
Clicking is kind of funny. Oh, it's just slow.
Yeah, you can speed it up with the speed. And okay, so this is how move to works. They move with a certain velocity, and I'm gonna weave in here. We could set the velocity of people using a control. Although I think I'm going to do that. I'm going to change it. We could set people's velocity so they go at different speeds. We could readily do that.
I'm getting runtime Java language, runtime exception, root population encoding valid value of argument for the line.
Oh, neat. Okay, that's interesting. Okay, could I see that? Okay, so can I see your?
Sure.
So it looks like it's giving some error messages back here. Okay. Okay, yeah, I don't see a problem with that. Okay, let's try this again. That's really interesting. Okay.
You're amazing. Thank you.
No.
We don't know what that was.
It's very strange. It's very strange. Every time I go to someone's computer to reproduce a problem, it always goes away. Yeah. Okay. Man, that would suggest I might not be a bad hire for some purposes. Okay, now can we replicate me about 1,000 times? And okay, so this is a move to. Let's address Maria's question. Why doesn't it just jump there? Well, there's a separate way of doing that. Let's go down in the person, down to advanced, and let's do, instead of move to, let's do jump to, okay? Jump to. Jump to will behave in much the same way, except it will jump. We can either specify that people have a velocity, a limited velocity, and they move at a certain, so in that velocity limits their time, so they move over time towards that location, or we can get them to jump there. So here by clicking, we're getting them to jump around, right? Okay. So this is great. So we've just seen the basic mechanisms. We can use move to and jump to move around. Any questions on that before we go and redo this next little bit? Yeah.
How does it handle, if I noticed that you specified a size for your grid.
Yes.
So if it goes, because you have a normal distribution, if it goes outside
yes.
of that, does it just still make it go to infinity, or does it function?
Yeah, no, It'll make it go towards to infinity.
So that scale of n main
Yeah.
is really for what? Space dimensions?
The sort of where to lay them out originally. Yeah. So they can diffuse. Okay. Let's ladies and gentlemen.
Can you just go back one more time and show the option that you selected to get them to jump?
Oh, sure. So we go to this, and we're going to get them to, we're going to click here under Advanced, and, excuse me, we have to click on this little thing here. Click on their visual representation, go to Advanced, and it's Jump to rather than Move to.
Okay.
Is that helpful?
Yeah.
Okay. Okay, folks, let's change that back to Move to. Okay. And now I want to take this. We're in a ladder. We're climbing up a ladder of learning. The ladder of learning. The boot camp ladder of learning. Okay. Okay. So now I'd like you to go to Person, and I'd like you to go add in a state chart. And the state chart is going to be particularly easy. This will be called Mobility State Chart. And Priyasri should note this. I'm going to add in a mobility state chart where I'm going to add in a state that's called in motion. Okay? See that? In motion. And then we're going to add in a self transition from in motion to itself. And this transition is going to be called arrival. And what sort of transition do you think this will be? It'll be agent arrival. Okay? And you notice the flag there. It's sort of like a speedway flag or something. Okay?
Excuse me, what's the key combination to then that transition line?
You just double click on it, and it will bend the curve. Is that okay? If you double click on a little white sort of blivet will occur. Okay. Okay, now this is going to be the key thing. You're going to paste in the code that you had earlier for when you on-click. You're going to paste it in for the in motion. Okay?
For the transition?
For the entry handler for in motion. That's important. Except I want you to switch it to, instead of being 100 to 20 for this, okay? So we're having it move to with distance 20, okay? So a standard deviation of 20. What do we expect to see? This is in person. What do you think we'll see? Okay, and then what will happen when they arrive there? Okay, shall we run it? Do people want me to stop and look at that more? It was 20. You should see something like this. And let's speed it up. Okay, so now we're having these agents move around in a somewhat random way. We're using this move to move around. Okay, people comfortable with that? Okay, does anyone want me to show some of the code? Okay, so yeah, they are spreading, and this is was actually inspired by Maria's question. Are they bounded to that box? Most emphatically, No, oh, you can't see it up here. They've leaked out of that box, and they're wriggling outside. Okay? Okay. The health applications of that are not entirely elucidated, but the basic mechanism will put us in good stead. Okay. Mobility is quite central to many of potential applications of agent-based modeling. Think about modeling people's movement through neighborhoods, exposure to certain influences, resources, messages, tobacco billboards, point-of-sale promotion of tobacco products, people's smoking outside of office places, or fast food restaurants. Think about exposure to air pollution in certain regions. Capturing mobility is quite important for certain types of health issues. And the basic mechanism, while fairly stylized, we've used here, carries over to that. Okay, so let's finish this example where we started. Let's go back to main and let's go click on that rectangle. And we're going to use the knowledge we've built up so that when we click on it, we'll have all the agents converge on ourselves. Okay? Okay. So we want, for every agent, we want to do what to it? You notice that it tells us something here. It says use click X, click Y, the coordinates of click. Okay? So that's going to be the coordinates where we've clicked. How can we tell all the agents to move to head towards that? Okay. Good. Okay. This is in the rectangle in the population. So we have to somehow go through every agent in the population. So we're going to introduce this for construct for person P. We're going to name each person P in the population. We want to do what to them? We have their name be P. What do we want to write? What do we want P to be asked to do? Move to. And how do we ask P to move to? How do we direct that move to request to P? Sorry? P dot move to. Thank you. P dot move to. We're going to move it to click X, click Y. That's the information provided to us. That's what this said. Click X, click Y. Click X, click Y. Okay? So let me put this on the big screen. Oh. Sure. It's in the click on the rectangle, the on-click of the rectangle. This is what we have.
Click on the rectangle.
So it's the on-click event of the rectangle. So it's in the advanced, yeah. And then this goes in there. So okay, so this is saying for each person in the population, calling them P. For each successive person in the population, we're going to call them P in turn, and for that person P, we're going to address P, move to this certain place. Move, and really what this means is move to is move towards, right? Like start heading towards. And when they get there, they'll arrive there, okay? Is that okay? Are you clicking atop an agent? Are you clicking atop the... Okay, yeah, you'd have to have it print something out to see when you click. You could have it print something out saying, hey, I heard a click. Just see, okay? It would be to click on the rectangle. You're going to have to click on the rectangle, yeah.
But they're still moving on their own.
Yep, they'll move on their own, but then when you click here, they should all converge, right? But once they all get there, now they're going to start jiggling it again.
Mine will converge so nicely.
Like that?
They start moving. No, I don't have as good as that. Definitely. So mine has come towards my clicks, but then not. So like, yeah.
Okay, let's just rehearse what we've done. So we've gone to this thing here, and we've on the rectangle in main, we've scrolled down and we've gone to advanced, and we've put the code here that's shown up on the big screen.
And what you have is in the oval of the person, you still have any code there in the oval?
Oh yeah, all the code that was there before. Okay, can I see the? I'd like to see dysfunction. Sorry? Yeah, that shouldn't matter actually for the person. That's okay. That shouldn't.
That shouldn't matter.
Could I see it?
Yep.
What does it do?
Fun
But different fun stuff.
I've got disobedient ducks.
Okay.
No, it's actually doing it. It's converging.
Oh, that looks really interesting. Okay, they're doing a disjointed jumps. Okay, yeah. That doesn't look too bad. Okay, let's okay, yeah. Oh, okay. So somehow, what's going on is, let's go look here. Oh, I see the problem. That's the problem. It's a timeout. It needs to be an agent arrival. Okay. So folks, various interesting dysfunction can be imposed upon this model by slight mistakes. One of them is this needs to be an agent arrival transition, right? It's when the agent arrives at its destination, rather than because what they're doing is they're like they're exhibiting, tick-like behavior, because like every second they're like going in a totally different direction. They're like, their goals change wildly, fluctuate wildly from second to second. No, okay. So what you should see is something kind of like this, right? When they get to their destination, they start to diffuse again. Oh, well, I just spit it to 25 times. I mean, if you want it, you can. Okay.
Wait, what happens? So mine gets to their destination and then they don't convert like yours.
Okay. Well, again, do you have that agent arrival?
We fixed it. I thought we fixed it. Is it just the one?
The agent arrival. That's right. And here, this is actually click on this thing. Yeah. Entry action. Okay. Jump. Oh, okay. Make that move to.
Get it back to move to.
Yeah. Okay. Try that again. Yeah. Okay. That's one thing. Yeah. Okay. Now go click in the background somewhere. Yeah. It's kind of hard. Oh yeah, that looks good. That looks much better. Yeah. Yeah. So I think the problem was that it was set to use jump to rather than move to. Okay. So ladies and gentlemen, we've seen a rather visceral depiction of some of the functionality associated with continuous movement, but the health applications of these observations are indirect. So we're going to be switching to a modality which builds on this knowledge in a way that simulates people's movement between different destinations and their exposures in different environments. So I'd like you to close out. Any questions on this? Anyone need TA help? Okay. How many people want more examples like that? Okay. Okay, so let's close it. Yeah. Okay, good. So the next little example will build on our knowledge here. So what I'd like you to do is I'd like you to create a new model. Okay. And this new model will be associated with a depiction of several different environments, and it'll exhibit continuous mobility between those environments. Okay. I should probably stop my recording and start it.